Welcome, dear students. So today we are going to derive the air standard efficiency of Otto cycle. So this Otto cycle is the working cycle of petrol engine. So already in the introduction section we have discussed what are the different assumptions of air standard cycle, etc. So in that we have seen that in air standard cycle air is the working fluid and our system is considered as closed system. So what will be the different process in Otto cycle? In an actual petrol engine we will have suction, compression, power and exhaust, but since this is a closed system, for Otto cycle, that is for air standard efficiency, we will not consider any suction or exhaust, etc. So we will start by compression. So the four processes in Otto cycle are: first one, that is process from 1 to 2, from one state 1 to state 2, is reversible adiabatic compression. Reversible adiabatic compression. So the air is compressed to a high pressure, its volume decreases and temperature increases. Then second one is heat addition. So in heat addition, petrol engine heat addition is done at constant volume. So 2 to 3, the next process will be constant volume heat addition. Since the spark plug in actual petrol engine, it is done by a spark plug and it is completed in microseconds or a very small time. So at that time our piston position will be at a particular volume. So that is why it is considered as constant volume heat addition. Then we have next process, that is 3 to 4. It is just the opposite of first one, that is reversible adiabatic expansion. So this is corresponding to the power stroke of an actual engine. So we have reversible adiabatic expansion. And finally we have heat rejection. Since this is a heat engine, so heated without any heat rejection, by second law of thermodynamics we cannot produce work continuously. So we have to reject the heat. So that is done in the last process, that is 4 to 1, and that is the opposite of second one, constant volume heat rejection. So we have to first understand or first consider these four processes, then only we can identify the cycle and its efficiency. So first process is reversible adiabatic compression. So air is compressed, pressure and temperature increases, volume decreases. Then that air we are adding heat with the help of an external source and at constant volume. Then we are producing work by expansion of that air, and finally we are rejecting heat at a constant volume. So you can see here in this 1 and 3 are just the opposite, and 2 and 4, similarly 2 and 4 are just opposite. So that is how the Otto cycle processes are constituted. Now in the next step we have to draw the PV diagram and TS diagram, that is pressure volume diagram and temperature entropy diagram. So first we have to draw the PV diagram. So in the y-axis we have pressure. So y-axis we will have pressure, and the x-axis we have volume. So how to draw this? First one is compression. So where we have to start, or in what direction we have to draw. So we know that in compression, pressure increases and volume decreases. So it should be in a direction like this. So in this direction you can see the pressure is increasing y-axis, and x-axis it should be decreased. So this must be, first process must be in this direction. And what is the shape of that compression? Because we know that it is adiabatic. So adiabatic process, we have this equation, PV raised to gamma is a constant, and this is the equation of a hyperbola. Xy is a constant, that is a equation of hyperbola. So which will be a hyperbolic curve. So we can draw like that. So we can mark 1 here. This is the starting of our process, and from 1 to 2 it will be like this, a hyperbolic curve where compression takes place. So this will be 1 to 2. So our 2 will be here. So this is 2. Now what is the second process? It is constant volume heat addition. So that is very easy, because in the x-axis we have volume. So if you consider the x-axis, it's here, this is our x-axis, and this volume must be constant, means it's a line parallel to the y-axis. So that will be a vertical line. So our 2 to 3 will be like this. This is our 2 to 3. So our 3 will be a very high pressure and temperature. So this is our 3. So this is 3. Then the remaining is very easy, because it is just the opposite of first and second. So what is the next process? 3 to 4 is an expansion. So expansion means pressure decreases, volume increases. So it is the opposite of 1 to 2. So it is again a adiabatic expansion. So it will be a hyperbolic curve again, and it will be in this direction, that is volume increases, pressure decreases. So we can draw like that. So it will be a curve. So this you have to draw in a hyperbolic curve like this. So this is our 3 to 4. And the thing you have to remember is the last process is again constant volume heat rejection. So that will be again a vertical line, and should come to back to 1, as this is a cycle. This process must be repeated. So this again we have a constant volume line which comes to 1. So our 4 must be on this line, that we have to take care of. Then only the 4 to 1 will be a constant volume process. So our 4 is this point, because it is a 4 to 1 will be constant volume heat rejection. So 4 to 1 is constant volume heat rejection. So we can just join 4 and 1 with a vertical line. So it is the opposite of 2 to 3. So this will be our 4 to 1. So we have drawn the PV diagram. Remember, 1 to 2 pressure increases, volume decreases like this. Then 2 to 3 we have a vertical line, constant volume heat addition. Then 3 to 4 is just the opposite of 1 to 2, another hyperbolic curve coming down in the right direction. And finally we have 4 to 1 constant volume heat rejection. So this is our PV diagram, and in this we can mark Q1 and Q2. Q1 is the heat addition. Normally Q1 represents in thermodynamics the heat added to the system, and Q2 is heat rejected. So this is heat added and this is heat rejected. So where it will be there, where is the heat addition process? It is 2 to 3 constant volume heat addition. So you can mark Q1 like this. Heat is entering or heat is added in this process Q1, and similarly heat is rejected in the 4 to 1 last process. So this will be Q2. So this completes our PV diagram. Next we have to draw in a similar way, that is TS diagram. So let's try TS diagram. So here temperature is in y-axis and entropy is in x-axis. So this is our temperature and this is our entropy. Here also where we have to start, 1 to 2 is a reversible adiabatic conversion. So its temperature must increase. So in 1 to 2 it's obvious that when compression, a gas is compressed, its temperature should increase. So it should go in the upward direction. But what about entropy? So for that we have this small equation in thermodynamics, that is for a reversible process entropy change ds is equal to dq by t. And we know that for adiabatic process this ds is, for adiabatic process, our first process is an adiabatic conversion. Adiabatic process dq will be 0. So adiabatic process dq 0. Then what will be ds when dq is 0? 0 by t is again 0. So ds is 0. So ds is 0 implies entropy is constant. So that is an important thing you have to remember. For a reversible adiabatic process, if any process is reversible adiabatic, its entropy must be constant. And it is known as isentropic process. So entropy is a constant, so it means isentropic process. So isentropy means entropy is constant. So we can now draw 1 to 2, that is, suppose this is our 1. We are starting from here, a low temperature and low entropy, and compression temperature increases, but it is an adiabatic, reversible adiabatic conversion, so entropy is constant. It is an isentropic process. So we can draw just a vertical line so that its entropy is constant. So this will be our 1 to 2. So see here, this is at a same entropy. 1 and 2 are at same entropy. Now what is 2 to 3? 2 to 3 is reverse heat addition at a constant volume. So what will happen when heat is added? Heat is added at a temperature. Heat is added at constant volume. So when heat is added, temperature is increases. That we know, when heat is added to a system, its temperature will increase. And entropy also increases, because we know entropy is ds is equal to dq by t. So in heat is added, dq will be a positive quantity. So ds also is a positive, so entropy will increase. And if you further write down its equation, this will be a logarithmic equation. So it will be a curve with increase in direction of both temperature and entropy. So it will be like this. So TS diagram will be a logarithmic curve in this direction, because as heat is added, temperature as well as entropy increases. So this will be our 3. So now we have reached to a very high temperature and entropy. Now again 3 to 4 is expansion, so temperature drops. So when a gas is expanded, temperature decreases. And again it is a reversible adiabatic expansion. So just like the first process, a reversible adiabatic process, entropy must be constant. So it is again a vertical line. So this third one is just the opposite of first one. So we have to draw like that. It's a vertical line coming down. So this will be a vertical line coming down in this direction. So this is 3 to 4. And our 4 will be somewhere here, a higher temperature than 1. And last one is just the opposite of second one, that is heat is rejected at constant volume. So when heat is rejected, dq is negative. So in thermodynamics, when heat is rejected, it is considered as a negative quantity. So ds will be negative. So that means entropy decreases, entropy as well as temperature decreases. And again it is a logarithmic equation if you go in detail. So that will be a curve opposite to the second one. So we can draw like this another curve, and which comes to 1 because this is a cycle. It should come to 1. So this is our last process, that is 4 to 1 reversible adiabatic expansion or isentropic expansion. And here also we can mark Q1 and Q2, that is in the second process heat is added. So this will be our Q1 and this is Q2, heat rejected. So this is Q1 and Q2. So that means we can now modify our first equation, that is reversible adiabatic combustion. It can be also written as this first process, it can be also written as isentropic combustion, because reversible adiabatic process means it is a isentropic combustion process. Similarly, the third one, reversible adiabatic expansion, means it is again an isentropic process, isentropic expansion. So first we have to explain these 4 processes, then come to the PV diagram, mark Q1 and Q2, and coming to the TS diagram again. Now we have to go for the derivation, that we have to derive the efficiency of the cycle. So we have to start from the basic equation. What is efficiency? What is the basic equation of efficiency of any cycle? This is the work net output by input. So it will be sigma W, that is the net work output getting from this cycle. Input is heat input, that is Q1. So Q1 is the heat input. So this we have to start from here. So this is output by input, just like any other system. Here also the efficiency we have to start from here. So this will be our equation 1. Now from first law of thermodynamics, first law is energy conservation. Energy can neither be created nor be destroyed. But when we are applying first law to a cycle by Joule's experiment, we have this expression, that is first law applied to, if you are applying first law to a cycle, first law of thermodynamics to a cycle, we have this expression sigma Q is equal to sigma W, that is the net heat transfer to the cycle is equal to net work transfer. So what is the net heat transfer in this cycle? So here we have only 2 heat, Q1 and Q2. You can see here only heat addition Q1, heat rejection Q2. So the net heat will be Q1. So net heat will be Q1 plus Q2 is considered as minus Q1 plus minus Q2, because in thermodynamics there is a sign convention used, that is in a system the heat entering is taken as positive and heat rejection is taken as negative. And similarly in thermodynamics, the work done by the system on surrounding is taken as positive and work done on the system is taken as negative. So we have to follow this sign convention. So we can see Q1 is heat entering to the system, heat addition to the system, it is a positive quantity, whereas Q2 is heat rejection, so it is a negative quantity. So Q1 minus Q2, that is sigma W. So this will be our second equation. Now substitute 2 in 1. We can here also we have a sigma W. Substitute that and we can write efficiency equal to Q1 minus Q2 by Q1. It is equal to 1 minus Q2 by Q1. So this is a commonly used expression for efficiency in thermodynamics. Efficiency is equal to 1 minus Q2 by Q1. And this will be our next equation, that is equation 3. So this is equation 3. Now what will be our next step? We have an expression, standard expression for efficiency. Efficiency is 1 minus Q2 by Q1. So next we have to substitute Q1 and Q2 here. So what is Q1? Q1 is the heat added, and which process? It is added in constant volume. So we have constant volume heat addition, we have an expression, that is Q1 will be equal to mCV delta T. So mass into specific heat at constant volume. And what is the temperature difference when it from 2 to 3? Heat added at 2 to 3. So temperature difference will be T3 minus T2. So this will be mCV T3 minus T2. So this is our fourth equation. Now similarly we can write Q2 also, because Q2 is the heat rejected. Here you can see heat rejection, and it is in 4 to 1. So here while write here again it is a constant volume, so last one is constant volume, so it is same expression, that is mCV delta T, but temperature, the state values changes. So heat addition, we have temperature is increased from 2 to 3. Here temperature changes from 4 to 1. So one thing you have to remember is while writing Q2, we must write it as like that it is a positive quantity, because if you write like Q2 is mCV T4, instead of T4 minus T1, if you are writing it as T1 minus T4, it will be a negative quantity. But already we have given a negative sign here by sign convention, so Q2 should be a positive quantity. That is why Q2 should be written as a positive quantity, because already we have assigned a negative value here by following sign convention. So what will be Q2? Q2 will be mCV T4 minus T1. T4 is greater than T1. From this figure you can see T4 is greater than T1. So Q2 will be mCV T4 minus T1. So this is our equation 5. So we have obtained two equations in terms of temperature difference and mass and specific heat. Now substitute this 4 and 5 in 3. So we will get efficiency is equal to 1 minus Q2 is this one, mCV T4 minus T1, and Q1 is mCV T3 minus T2. So this we can cancel this mCV from numerator and denominator. So it will be 1 minus T4 minus T1 by T3 minus T2. This is our equation 6. But this expression, we have every term in terms of temperature. It is of no use to us because we want to derive the air standard efficiency and we have to express it in terms of some engine specifications. So important engine specifications are volume, its swept volume, clearance volume, etc. Or that volume we have to introduce here. So our next step will be to convert this temperature in terms of volume ratio. Then only it will be useful. Otherwise, we may not be able to measure the temperature of engine in every point. It will be very difficult because it is high speed machinery. So now next step is we have to convert this temperature in terms of some volume ratio. So for that we have to define the compression ratio. So already from this figure PV diagram we can define compression ratio. So what is compression ratio? Compression ratio is volume before compression divided by volume after compression. So it will be volume before compression divided by volume after compression, and this will be volume before compression. So how much volume is available before starting the compression? That is the first process, reversible adiabatic compression. Before starting we have V1 volume available, and after compression we have only V2 volume. So this will be V1 by V2. So this is equal to, so this will be equal to V1 by V2. And if you see the figure again, this V1 is same as V4 and V2 is same as V3 because we have two constant volume. So the Otto cycle works between two volume levels only, one this volume, one this volume. So this is same as V1 by V2 is same as V4 by V3. So this we have to use the conversion ratio. Conversion ratio normally denoted by R suffix K. You can use R suffix K for conversion ratio. So conversion ratio is V1 by V2, which is same as V4 by V3. So this we have to use. And in terms of engine, further you can see this volume between the volume between V1 and V2. This is swept volume Vs. The piston will be moving from between 1 and 2. So in an actual engine that corresponding to the swept volume. And this small remaining volume is the clearance volume Vc. So Vc is equal to V2. So these things we have to consider while solving the problem. Vs is in between 1 and 2, or we can say Vs is V1 minus V2, and clearance volume Vc is equal to V2. So now you can use this expression also, that is compression ratio. We can write compression ratio Rk of the cycle is equal to V1 by V2, which is same as V4 by V3. So this will be our next equation, that is equation 7. So this is equation 7. So we have to express somehow the air standard efficiency in terms of this compression ratio. Then only it will be very useful. So how to convert this temperature expression into these terms? That is our next step. For that we have to consider process 1 to 2. So first we have to consider. So consider the first process. Consider process 1 to 2. That is reversible adiabatic compression. So this is reversible adiabatic compression. So what are the equations available for this particular process? One is, it is an adiabatic process. We know that PV raised to gamma is constant, or we can write P1 V1 raised to gamma equals to P2 V2 raised to gamma. This is the equation holding for any adiabatic process, so we can use this here. And another equation, we have one more equation, that is, what is that equation? Because we are in this air standard efficiency, we are considering air as an ideal gas. It's a perfect ideal gas. So PV by T is a constant. Ideal gas equation is PV equal to MRT, or PV by T is a constant, or in terms of 1 and 2 we can write it as P1 V1 by T1 is equal to P2 V2 by T2. So this is two equation holding for first process, that is 1 to 2. One is for adiabatic equation, P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Another one is the equation of ideal gas, that is P1 V1 by T1 is equal to P2 V2 by T2. So we have this temperature expression. Now we have to convert that into volume expression. With the help of this, by combining these two equations, we have to somehow get a relation between temperature and volume, because we have to convert the temperature expression in efficiency into these volume ratio expressions. So that is how we have to do that. We have to eliminate the pressure. So by combining these two equations, somehow we have to eliminate the pressure and write the equation between temperature and volume. So for that, we can say from this equation we can write T2. What is T2 by T1? T2 by T1 will be P2 V2 by P1 V1. P2 V2 by P1 V1. And from first equation we can write this, or replace this P2 by P1. Now somehow we have to replace this pressure, then only we will get a relation between temperature and volume. So what is this P2 by P1? From this equation we can write P2 by P1. What is P2 by P1? P2 by P1 will be equals to V1 by V2 raised to gamma. So we can write it as V1 by V2 raised to gamma. So substitute this here. So that means T2 by T1 is equals to V1 by V2 raised to gamma into V2 by V1. So V2 by V1 we can write it as V1 by V2 raised to minus 1. So that will be, further simplifying, T2 by T1 is V1 by V2 raised to gamma minus 1. And from equation 7 we can write it as this V1 by V2 is combustion ratio RK. So from equation 7, this is same as RK raised to gamma minus 1, because V1 by V2 is the combustion ratio RK. So this is our next equation, that is T2 is T1 RK combustion ratio raised to gamma minus 1. So this will be our another important equation. Next equation, that is equation 8. So this is equation 8. So we have obtained a relation between temperature 1 and 2 in terms of combustion ratio. So similarly, next we have to derive an expression between 3 and 4. Then we can solve the further. So for that we have to consider the next process, that is again 3 to 4, reversible adiabatic expansion process. Just like a similar way we can have an expression like that. So this will be reversible adiabatic expansion. So we have two equations here also. It is an adiabatic process. So we have P3 V3 raised to gamma equals to P4 V4 raised to gamma. That is one expression. Another one is the ideal gas equation, that is P3 V3 by T3 equals to P4 V4 by T4. Now somehow we have to eliminate pressure just like the previous way. So by combining these two equations, so from this equation we can write T3 by T4 or T4 by T3. We can write it as T3 by T4. So T3 by T4 is P3 V3 by P4 V4. So this is P3 V3 by P4 V4. Now what is this P3 by P4? P3 by P4 we will get from this first expression. So from this we will get P3 by P4, that is P3 by P4 is V4 by, so from this expression we will get P3 by P4 as V4 by V3 raised to gamma. So this will be V4 by V3 raised to gamma. Now substitute that here. Combining this, we can write it as T3 by T4 is, it will be V4 by V3, V4 by V3 raised to gamma into V3 by V4. V3 by V4 is V4 by V3 raised to minus 1. Now what is this V4 by V3? That is the combustion ratio. So if you look at the combustion ratio expression here, V4 by V3 is again combustion ratio RK. So this is same as T3 by, this is combustion ratio, V4 by V3 is combustion ratio. So T3 by T4 is again combustion ratio raised to gamma minus 1. So RK raised to gamma minus 1. Or we can write it as T3 equals T4 into RK raised to gamma minus 1. So this is our next equation, that is equation 9. So this will be our equation 9. So we have completed, so we have expressed T1 in terms of T2 and combustion ratio, similarly T3, T4 in terms of combustion ratio. Now we have to substitute 8 and 9 in the temperature expression, that is in equation 6. So substitute this equation 8 and 9 in 6. So we will get efficiency is equal to 1 minus, what is equation 6? Equation 6 is this, efficiency is 1 minus T4 minus T1 by T3 minus T2. Now what is, so here we have T4 minus T1. Now what is T3? Sorry, T4 minus T1. So here we have T4 is equal T4 minus T1 in the numerator, that we will keep it as such. And denominator we have T3, but T3 is from equation 9, T4 into combustion ratio raised to gamma minus 1 minus T2. T2, what is T2 from equation 8? Equation 8, this T2 is T1 into RK raised to gamma minus 1. So this will be T1 RK raised to gamma minus 1. So you can see here the numerator and denominator both have T4 minus T1 as a common term. So you can take this RK raised to gamma minus 1 outside. So 1 minus 1 by RK raised to gamma minus 1. And these terms will cancel because numerator also we have T4 minus T1. Denominator will also have T4 minus T1. So these will get cancelled. So our final expression for efficiency of Otto cycle is, it's a simple expression, that is 1 minus 1 by RK raised to gamma minus 1. So this is the important expression for air standard efficiency of Otto cycle. And what are the inference we are getting? So one inference is as combustion ratio increases, theoretically as combustion ratio increases, you can see this term will decrease, this minus term will decrease when combustion ratio increases. So efficiency will also increase. So that is theoretically if the combustion ratio of a petrol engine increases, its efficiency will increase. But we know that practically the petrol engine combustion ratio is not that much high compared to diesel engine. It is in between 6:1 to 12:1. Why we are limiting it to 12:1? By this equation we can increase further and further so that we will get more and more efficiency. But it is due to the practical limitation of petrol engine, that is knocking by Otto ignition. So if you increase the combustion ratio of petrol engine beyond this value 12:1, if you go for 15:1 or higher than that, an abnormal combustion known as knocking will happen in petrol engine, and it will reduce power and it will have several drawbacks. So that is why we have to limit the combustion ratio of petrol engine to 12:1. Otherwise, by this expression, as combustion ratio increases, its efficiency will be higher and higher. So that is the important thing you have to note down. And another one is, if you increase gamma value, this efficiency will also increase. So for increasing gamma value, you have to go for some gas like helium, etc., which is having more gamma value than air, but that is not practically possible. So with this, we are stopping this air standard efficiency of Otto cycle. Thank you.